If you look inside a modern quantum computer, you see this. It is often called the golden chandelier. It is a stunning, meticulously engineered structure, featuring intricate tiers of metal that suspend the actual computing hardware at the very bottom. But to the researchers actually building these machines, this beautiful array of wires represents a massive failure in design. They call it the wiring catastrophe. The bottom of the chandelier must be kept near absolute zero, yet every physical wire acts as a straw, pulling room temperature heat from the outside world directly into that freezing void. Today, running a 1,000-qubit machine requires somewhere between 3,000 to 5,000 physical coaxial cables to bridge the external racks to the quantum core. It looks like a dense, unmanageable bowl of metallic spaghetti. Because every single one of those cables is a thermal bridge actively leaking heat into the system, the architecture itself fights the machine's survival. The core unit of this computer is the qubit. Unlike a standard binary bit, a qubit can exist in complex superpositions of states, which gives the machine its power. But that superposition is incredibly fragile. The slightest introduction of heat or thermal noise instantly collapses the calculation. To build a fully fault-tolerant quantum computer capable of solving real-world problems, engineers need to scale up to tens of thousands of qubits. If they try to do that using the current chandelier model, the sheer thermal load of tens of thousands of cables would literally melt the refrigeration system. The physical math is unforgiving. If engineers cannot figure out how to control these fragile qubits without physically wiring them to the outside world, quantum computing will permanently plateau in the laboratory. The solution to this thermal bottleneck is drastic. Engineers are now abandoning the cables entirely, taking the control electronics that normally sit outside the machine and moving them inside the refrigerator. Let's look at the quantum stack architecture. At the bottom is the quantum plane. Above that is the interface layer. By moving cryo-CMOS chips into that middle layer, the system generates microwave pulses internally. These chips sit at 4 Kelvin, firing instructions without external wiring. Operating in that environment introduces a severe physical constraint. The 4 Kelvin stage of a dilution refrigerator possesses only 1.5 watts of total cooling capacity. That means these entire silicon control chips have to operate on less power than a single birthday candle. Embedding the control brain inside the fridge sidesteps the physical wiring catastrophe, but it forces the system to operate under terrifyingly strict power and environmental limits. The problem is that standard silicon was never meant to function near absolute zero. Its physical properties shift in the cold. Every time the temperature fluctuates even slightly, the embedded chips behave unpredictably, causing what engineers call calibration drift. Combining that drifting control hardware with the inherent noise and error rates of the qubits themselves, you end up with a highly unstable system generating millions of constantly fluctuating parameters. The sheer volume of these minute shifts makes manual control impossible. Human engineers and even standard classical software programs are completely incapable of monitoring and recalibrating that much chaos in real time. By solving the thermal problem, engineers have created a control environment so complex that traditional programming is entirely useless to run it. This forces researchers to look to the very top layer of the quantum stack. The only tool fast enough and complex enough to orchestrate the interplay between those freezing cryochips and the raw qubits below is artificial intelligence. This schematic outlines AI applications in a quantum system. In Panel D, machine learning acts as an automated mechanic, learning noise patterns to fix calibration drift. Meanwhile, Panel A shows reinforcement learning models rearranging quantum gates to avoid hardware bottlenecks. Finally, AI steps in as a real-time error decoder. It constantly reads the system to predict and mitigate inherent quantum state collapses far faster than any classical algorithm could manage. AI acts as an active, real-time defender, constantly adjusting the physical environment to keep the fragile quantum states from dying. The popular public narrative predicts that quantum computers will eventually build infinitely smarter artificial intelligence. In the laboratory, the reality is reversed. Classical artificial intelligence is the absolute prerequisite required to build and operate a functioning quantum computer. The future of computing depends on both a golden chandelier and a hostile, freezing microchip. an environment that only an AI mind is fast and complex enough to orchestrate.